Então, toda vez que você faz uma estrutura de Lewis, você...
Oi, pessoal, tudo bem? Eu sou a Natália, sejam como exemplo a molécula de CO2. E o dióxido de carbono tem duas estruturas de Lewis possíveis, uma com oxigênio como átomo central e a outra com carbono como átomo central. Vou deixar aqui na descrição do vídeo, nos comentários, links aqui do canal sobre estruturas de Lewis, sobre como construir estruturas de Lewis de maneira bem fácil. Bom, para o CO2, a gente tem essas duas possibilidades de estrutura, mas para que a gente possa determinar a carga formal sem auxílio de fórmula, há necessidade da gente saber, ter consciência de elétrons de valência desses átomos envolvidos, do oxigênio e do carbono. Na tabela periódica, a gente consegue verificar que o carbono tem número atômico 6 e o oxigênio número atômico 8. Nós vamos fazer aqui então, ó, carbono é 1s2, 2s2, 2p2, seus 6 elétrons, e o oxigênio 1s2, 2s2, 2p4. E aí a gente consegue, com a configuração eletrônica, saber o número de elétrons de valência de cada um. 4 para o carbono e 6 para o oxigênio. São essas informações que nós vamos utilizar para calcular a carga formal sem fórmula. O que a gente vai considerar então? Que o oxigênio isolado tem 6 elétrons e o carbono 4. Tudo aquilo que destoar disso, né, se o oxigênio ou o carbono na ligação química estiver com elétrons a mais ou a menos, vai influenciar na carga formal. Então, nós vamos começar pela estrutura número 1. Na estrutura 1, nós temos do lado esquerdo o oxigênio fazendo duas ligações, só que ela é 100% covalente. Ou seja, se eu tenho 4 elétrons sendo compartilhados, 2 elétrons são do oxigênio da esquerda e os outros 2 são do oxigênio da direita. Então, o oxigênio, especificamente aqui do lado esquerdo, está com 2 elétrons aqui da ligação, mais 4 elétrons que são pares isolados. Como consequência, ele tem um somatório de 6 elétrons. Esse oxigênio tem o mesmo número de elétrons dele isolado, ou seja, 6 elétrons de valência. Então, nesse caso, a carga formal será zero, porque ele tem os 6 elétrons dos 6 requeridos para ele ficar com a valência original. Já o oxigênio do meio está compartilhando 2 elétrons do lado esquerdo e 2 do lado direito. E aí, o que vai acontecer com esse oxigênio? Ele está com 4 elétrons de valência e ele deveria ter 6. Então, ele está com um déficit de elétrons. Então, a carga formal, nesse caso, ficará mais 2 para o oxigênio no centro. O que acontece então com o carbono? O carbono deveria ter 4 elétrons de valência, mas ele está fazendo duas ligações, ou seja, ele fica com 2 elétrons aqui, mais 2 pares isolados, ou seja, ele está com um total de 6 elétrons de valência. Ele deveria ter 4 e está com 6. Ele está com uma sobrecarga de elétrons, vamos chamar assim. Então, a carga formal no carbono está como menos 2. Na estrutura do lado direito, vou colocar estrutura 2, nós temos o carbono como átomo central. O oxigênio do lado esquerdo está com os 2 elétrons da dupla, que está sendo compartilhado com o carbono, mais os 2 pares isolados, num total de 6 elétrons de valência. Ou seja, ele tem 6 elétrons de valência quando está ligado e 6 quando está isolado. A carga formal resultante aqui é zero. Vamos falar agora do carbono. O carbono ele está fazendo 4 ligações, portanto, ele tem 4 elétrons de valência. Quando ele está isolado, ele também tem 4 elétrons de valência. Então, eu não tenho residual de carga. O que acontece aqui é que a carga formal será zero. 4 elétrons de valência, 4 elétrons na ligação. Então, para o oxigênio do lado direito, nós temos o mesmo ambiente eletrônico do oxigênio do lado esquerdo. Ele vai ficar com 2 elétrons relativos às ligações e mais 2 pares desse lado. Então, eu fico com 6 elétrons de valência também para o oxigênio da direita. A carga formal dele será
Olá, se tá na família 6A, tem 6. Só que são 3 oxigênios. 3 vezes 6, 18. Mais 5, 23. Mais uma carga negativa do ânion, 24. Agora, organizamos os átomos de forma simétrica e depois os conectamos por ligações simples. Com isso, já foram distribuídos 6 elétrons das ligações. Agora, distribuímos os 18 elétrons restantes em pares isolados. Observe que cada oxigênio obedece à regra do octeto, mas o nitrogênio não. Ele possui apenas 6 elétrons das ligações ao seu redor. Sempre que isso acontecer, transforme um par de elétrons em uma ligação dupla. E você pode escolher aleatoriamente. Eu vou remover esse aqui e fazer a dupla ligação para chegar à estrutura de Lewis do íon nitrato. Finalmente, expressamos a carga negativa do ânion. Agora, cada um deles obedece à regra do octeto e os 24 elétrons foram devidamente distribuídos. Obrigado por assistir, um abraço e
Hi, this is Dr. B. Let's do the SO3 and the I4. And then we have 2 left over. We'll put them right here on the central atom. So we've used all 26 valence electrons. And the structure looks pretty good. Each of the atoms has an octet. We've used the 26 valence electrons. So this is a possible structure for the sulfide ion, SO3 2-. Since sulfur is in the 3rd period on the periodic table, it can hold more than 8 valence electrons. So we should check our formal charges here to see if this is the best structure. For the sulfur on the periodic table, it has 6 valence electrons. We have here on the Lewis structure 2 non-bonding, and then these right here are all involved in bonds. So 6 over 2. 6 minus 2 minus 6 over 2 is a positive 1 for the central sulfur. sulfur. For the oxygens, and they're all the same, so we'll just do one on the periodic table, 6 valence electrons. Non-bonding, we have 6 non-bonding for each of the oxygens, and then 2 bonding. 6 minus 6 minus 1 gives us -1 for each of the oxygens. So this makes sense. I have a +1 here, and then 3 of the -1s, and that all adds up to -2. So this makes sense as a structure, and I can put brackets around it and show that it is indeed an ion. I see this +1 here on the central sulfur, and I know if I pull a pair of electrons from the oxygen and form a double bond, that'll go to 0. So I'd like to try that and see what it looks like. So here I've taken these 2 valence electrons out here, and I've moved them in to form a double bond with the sulfur. That results in this oxygen here and the sulfur now having 0 for their formal charge, and these remain at a -1, which makes sense. We have a -1, -1. That keeps our -2 right here, and we've still used the number of valence electrons that we were initially given. So this may actually be a better Lewis structure for SO3 2- because the formal charges, we have more formal charges at 0 than we did in the previous structure. So that's the SO3 2- Lewis structure. At the end of this video, you'll be a pro at drawing the basic Lewis structures. There really are only 5 main steps that you need to know. Let's get started. Step 1. Find the total number of valence electrons for the molecule you're drawing the Lewis structure for. Let's try one. We'll use the periodic table to figure out how many valence electrons each element has. Hydrogen is in group 1 on the periodic table, so it has 1 valence electron, but the subscript tells us that we have 2 hydrogens. So we'll need to multiply that by 2. Oxygen is in group 6, or 16. It has 6 valence electrons, and when we add that up, 2 plus 6, we get a total of 8 valence electrons for H2O. Remember, valence electrons are the outer shell electrons. They're the ones that form chemical bonds and interact with the world around them. Let's try one more, cyanide. For cyanide, we can look on the periodic table again. Carbon has 4 valence electrons, and nitrogen has 5. The trick for this one is, though, it's a negative ion. This negative sign right here tells you that there's going to be 1 extra valence electron. So 4 plus 5 plus 1, 10 valence electrons for the cyanide ion. Step 2. Put the least electronegative atom in the center. So how do you know it's the least electronegative atom? Just remember that fluorine is the most electronegative, followed by oxygen. So as you move away from fluorine and oxygen, atoms become less electronegative. That means those atoms will go at the center. Let's see how it works. When I draw the Lewis structure for something like NO2, I can see that nitrogen is further away from fluorine than oxygen. That means when I draw my Lewis structure, I'll put nitrogen at the center and oxygens on the outside. For something like PCl3, I can see that phosphorus is further away from the fluorine than the chlorine atom. So I'll put phosphorus at the center and the chlorines on the outside, like this. Some Lewis structures, like HCl, only have 2 atoms. In that case, you don't have to worry about it because there's no center. An important note, hydrogen always goes on the outside of Lewis structures. Always. Seriously. Let's look at HCl again. We know it has 8 valence electrons, and we'll put the first 2 in our structure between the H and Cl to form a chemical bond. That's important. By putting those 2 electrons there, we're showing that the hydrogen and the chlorine are chemically bonded now. Step 4. Complete the octets on the outside atoms. Octet means 8. For HCl, we have a total of 8 valence electrons, 1 for the hydrogen, 7 for the chlorine. So we've used 2 already to form the chemical bond. For the chlorine, we'll put 4, 6, and then 8. We've used all the valence electrons, and we've completed the octet for chlorine. It has 8 valence electrons. For basic Lewis structures, the big exception is going to be hydrogen. It only needs 2 valence electrons for a full outer shell. So hydrogen has a full outer shell with 2 valence electrons. The chlorine its octet is full with 8, and we've used only the 8 valence electrons that we have for the HCl molecule. We're done with this structure. There's one more rule that we need to look at. It doesn't apply to HCl, and actually it doesn't apply to a lot of molecules. But what happens when you've used all your valence electrons and you still haven't completed the octets for each atom in the molecule? That's step 5. So sometimes you run out of valence electrons and still haven't filled the octets. Hey, it happens, right? So in step 5, what we're going to do is if we run out of valence electrons, we'll move some of the valence electrons from the outside to the inside and share them and form double and triple bonds. Here's how it works. So for O2, oxygen, if I follow all the rules, I count the valence electrons, I have 12, and if I put a bond between the atoms and then fill the outer shell, I end up with the situation where I have an octet for this oxygen, it has 8, but this oxygen only has 6 valence electrons. It doesn't have an octet, and I don't have any more valence electrons. To solve the problem, I can take these valence electrons right here and move them to the center to share them and form a double bond between the two oxygen atoms. I'm still only using 12 valence electrons, but now this oxygen has 2, 4, 6, 8 valence electrons, and this oxygen has 2, 4, 6, 8 valence electrons. So by sharing those valence electrons, I can get the octet on each of the oxygens and still use the 12 valence electrons that I had for the O2 molecule. If I wanted, I could replace these right here with 2 lines to show the double bond, where each line represents a pair of electrons. For Lewis structures like N2, I would even use a triple bond to achieve octets. So how do you get good at drawing Lewis structures? Well, the first thing is know the steps. They're your guide. The second thing is practice. You need lots of practice to get good at this, for it to be second nature. Use the links in this video or go to my website and try more videos.
In this video, I'll explain how to do these 9 Lewis structures.
I'll be helping another YouTuber. From there, you would see, okay, which one is the least electronegative compared to chlorine. A single is by itself. Yeah, 6 electrons, 3 lone pairs. 16 before atom. And I know but just be a this has
structures. The way to use the video, do one of the Lewis structures, and then you have the time underneath it. Go to that place in the video and check your work. When you're done, go back and do some other ones. They'll get harder as you go on, and that's to help you learn more complex Lewis structures. Just a quick note, whenever you have a pair of electrons like this, that's called a single bond. And we can write a single bond also is just by putting a line like this. So in our NH3 Lewis structure here, we can replace the bonds, these are the pairs of electrons between 2 atoms, with single lines. And that'll mean the same thing. It's the same Lewis structure, just a different representation. We'll start with the Lewis structure for OF2. First, we find the valence electrons. So oxygen is in group 16, sometimes called 6A. It has 6 valence electrons plus fluorine, which has 7. But we have the 2 fluorines, so we'll multiply that by 2. And that gives us 6 plus 14, a total of 20 valence electrons. Next, we'll put the least electronegative atom in the center of the Lewis structure. That's going to be our oxygen, and then on either side, let's put the fluorine atoms. We'll place a pair of electrons between the fluorine and the oxygen here to form a chemical bond, and then over here. Once we've done that, we'll complete the octets around the fluorine atom. So we'll want to have 8 valence electrons around each fluorine atom. So now the fluorines have 8 valence electrons. They have an octet. We've used 16. That means we have 4 more valence electrons. We'll move back now to that central atom. We'll put 2 valence electrons here, and then 2 here. And we've used all 20 valence electrons, and each of the atoms in this Lewis structure has an octet. So we're done with the Lewis structure for OF2. For the CH4 Lewis structure, let's find the number of valence electrons. Carbon is in group 14, sometimes called 4A. It has 4 valence electrons. Hydrogen has 1 valence electron, but we have these 4 hydrogens, so let's multiply this by 4. If we add that up, 4 plus 4 equals 8. So we have 8 valence electrons for the CH4 Lewis structure. We'll put the carbon in the center. Hydrogen atoms always go on the outside. So we'll put the carbon in the center, and then we'll put the 4 hydrogen atoms around it. Next, we'll put a pair of electrons between each of the atoms to form a chemical bond. So we'll put 2 here. At this point, the carbon has an octet. We've used 2, 4, 6, 8. We've used all our valence electrons, and the hydrogens, they each have 2. This is an important rule. Hydrogens only need 2 valence electrons to have a full outer shell. So the carbon has an octet, the hydrogens each have 2. We're done with this Lewis structure. H2 is probably about the simplest Lewis structure we can draw. So if we count the valence electrons up, hydrogen is in group 1. It has 1 valence electron, but we have the 2 hydrogens. We multiply those together. 1 times 2 is 2. So we have a total of 2 valence electrons. So we'll put our 2 hydrogen atoms right here next to each other, and then we're going to move 2 valences. So we'll put 2 hydrogens between them to form a chemical bond. And when we do that, we've used both of the valence electrons. Hydrogen has 2. We said that hydrogen is an exception. It only needs 2. And that's the Lewis structure for H2, hydrogen gas. CO2, carbon dioxide. Is a little bit more of a complicated Lewis structure, but it's not too bad. Let's count the valence electrons. We have 4 for carbon. Oxygen has 6, but we have these 2 oxygens. And that gives us a total of 4 plus 12, 16 valence electron. We'll put the least electronegative atom in the center of the Lewis structure, that's the carbon, and then we'll put an oxygen on either side. Next, we'll move electrons to the center to form the chemical bonds. Once we form those chemical bonds, we'll complete the octet around the oxygen atoms. We have a total of 16 valence electrons. And now we've completed the octets on the oxygen atoms. But we've used 16 valence electrons, and we don't have any more. The carbon in the center, though, it only has 4 valence electrons around it. It doesn't have an octet. To solve this problem, we can move valence electrons from the oxygen atom to the center between the carbon and the oxygen so that they share valence electrons. So when we do that, the oxygen atom, it still has 8 valence electrons, but now the carbon atom has 6. We're almost there. Let's take 2 from this oxygen, move them to the center. Now, this oxygen here still has 8. This oxygen has 8. And the carbon in the center has 8 valence electrons, and we're using all 16 of the valence electrons here, no more. So this is the Lewis structure for CO2. We call this a double bond. For the BH3 Lewis structure, boron has 3 valence electrons. It's in group 13, sometimes called 3. Hydrogen has 1, and we have 3 hydrogens. So we have 3 plus 3, total of 6 valence electrons for the BH3 Lewis structure. Since hydrogen always goes on the outside, we'll put the boron in the center, and then we'll put the 3 hydrogens around it. We'll start by putting pairs of electrons between atoms to form chemical bonds. We've created the chemical bonds, but we've used 2, 4, 6 valence electrons, and we only have 6 valence electrons. So how do we complete the octet for the BH3 Lewis structure? It turns out that with Lewis structure there are quite a few exceptions. The octet rule is a very general rule. It works a lot of the time, but not all the time. So for boron, it's one of the exceptions. Boron only needs 6 valence electrons. We'll see more of these exceptions later on. O3 is also called ozone. We have 6 valence electrons for oxygen, and we have the 3 oxygens for a total of 18 valence electrons for this Lewis structure. We'll write the 3 oxygen atoms and we'll just put them next to each other. So 1, 2, 3. Next, we'll put electrons between the oxygen atoms to form the chemical bonds. We've used 2, we have 16 more. Let's complete the octets on the oxygens on the outside. So we've used 16 valence electrons. We have 2 more, and we'll put those on the central oxygen. And we have octets on the outside, on the oxygens on the outside, but that central oxygen, it only has 6 valence electrons. So much like we did with carbon dioxide, we can move a pair of electrons to the center. When we do that, these 2 oxygens are sharing those electrons. So this oxygen has 8, the central oxygen has 8, and then this oxygen over here on the left also has 8. When we have Lewis structures like this, there's another way we could draw it. You can see the only difference here is we have the double bond here, and on this one we have the double bond on this side. These are called resonance structures. Often when we draw Lewis structures, you're asked to draw the resonance structures. Those are the different ways you can draw the Lewis structure. Here we have a double bond on the right, and here we have it on the left. We have something a bit odd with this Lewis structure, and that's that plus sign up there. Whenever you have a plus sign, it means the ion, the compound, it's positive. And to be positive, it lost an electron. So when we write up the number of valence electrons, nitrogen has 5 plus the 4 oxygens. We need to subtract 1 valence electron because the plus means we've lost one. If this were a negative sign, it would mean we gained one. So 5 plus 4 is 9 minus 1. We have a total of 8 valence electrons for this NH4 plus ion. We'll put the N in the center, hydrogen, always on the outside, and then we'll put the 4 hydrogens around it. We have a total of 8 valence electrons. Let's put a pair of electrons between each of the atoms, form a chemical bond. There. So we've used all 8 valence electrons. The nitrogen, it has a full outer shell, has an octet, and the hydrogens, they only need 2. They all have full outer shells. That's the Lewis structure for NH4+. It's called the ammonium ion. For SO4 the sulfate ion, sulfur has 6 valence electrons. Oxygen also has 6. We have 4 oxygens. And this 2 up here, that means we have an extra 2 valence electrons. So we'll add those right there. We have 6 plus 24, that's 30, plus 2 gives us 32 valence electrons for this Lewis structure. We'll start by putting the least electronegative atom in the center, that's the sulfur, and then we'll put the 4 oxygens around it. We have 32 valence electrons. We'll put 2 between each of the atoms to form the chemical bonds. Then we'll go around and complete the octets on the oxygen atoms. Whew, that was a lot of electrons. If we add all of these electrons up, you'll see that we've used 32 valence electrons. The sulfur has an octet, as do all of the oxygen atoms. It looks like we're done with this Lewis structure. Everything has octets. We've used all the valence electrons. It's all good, right? However, if you're in a more advanced chemistry class, you'll learn that sulfur and other atoms in the periodic table that are in period 3 or below, they can have what's called an expanded octet. An expanded octet means that the central atom there would have more than 8 valence electrons. The way we tell is we check the formal charges. I'm not going to do that right here, but I'll show you what the correct structure looks like after we find the best formal charges. This is actually the best Lewis structure for the sulfate ion. All of the formal charges are 0. Each of the oxygen atoms has 8 valence electrons. The central sulfur has 2, 4, 6, 8, 10, 12, but that's okay. It can do that because it's in period 3 on the periodic table or below. It can have that expanded octet. So this is the best Lewis structure for SO4 We should also put brackets around this with that 2- to show that it's an ion. And there you have it, the Lewis structure for SO4 the sulfate ion. For phosphate, we have 32 valence electrons. So checking the formal charges is a very good idea if you're in an advanced chemistry class. One last thing, we should put brackets around this since it is an ion, and then we'll write the 3 minus
8, right? 2, 4, 6, 8. That's 8 times 4 of them. Where, remember that an ion, valence electron. I'll have you do, I'm going to have you do practice problems after, but that's fine. Now that you've learned the steps to draw a loop.
Okay, so now we pick our central atom, which is going to be okay, so 14.
Good.
And now I pick my central atom.
Mm-hmm.
So because this is like one pair and then another, I guess it's just going to be carbon and then
Good.
like
Keep
carbon.
going. You're right.
Because it's a way, right? And the oxygen is gonna.
And then we're charged. So remember, this had to have been in brackets.
Oh. And then we put 2 minus on the outside.
Good. This structure, the throw. So I wanted to do this one for sure. Charges. Each in charge two would say part of our formula, where formal charges are equal to valence electrons. Understand to be able to select atom formal alone. It has to be one, and I say are in the. So that's why this. Is I would actually move these electrons and form a double bond. And I know that sulfur is part of that expanded octet exception, so it can have more than 8 valence electrons on it.
Yeah.
I'm going to try to get that balance to be 0. For I'd say like the more complicated ones, typically the ones that have charges, kind of like this, that is something I would check for. Yeah, definitely. But the previous ones that did follow the octet rule and they weren't part of any exceptions, then you don't have to worry about them.
Okay.
So I'm going to keep going with this. I'm going to see once again, all right, well, how many bonding electrons do I have now since I did change this? So I have, let's see, I just added one more here. So there's 1, 2, 3, 4, 5. Okay, there's 5. So 5 bonding electrons. There are still no lone pairs on the central atom. So then this is +1. Almost there. I'm not there just yet. I want this to be 0 for the formal charge. So again, I'm going to move these electrons here. And then I'm going to form a double bond. And I'll re-find the formal charge. So now that I change this again, I'm going to see, well, how many bonding electrons do I have now? Well, now I have 1, 2, 3, 4, 5, 6. Okay, great. That's 6 bonding electrons. Plus, I have no individual lone pairs. 6 minus 6 is 0. Yay, we finally did it. So we do have a 0 formal charge. That's happy. Now I'm going to double check the oxygens. And I'm going to see how are those formal charges, because every single formal charge of those atoms have to add up to the overall charge of this structure that they gave us. So a -2. So I'm going to do this again. So 1 now for -B. This is a single bond. It has the same number of 2, 0. We're doing do form how one side today.
1.
So going over that. The next one. Perfect. Okay. So the next ones I'm going to have you continue on right off the bat. Okay. But it will get faster. But
A lot of work. It's not like
it's a
hard,
lot of work. It's another -1 that gives us an overall -2 charge. So +1 plus 0 plus 0 plus -1. Really what we're doing is -1. So that's okay. +2 charge. Plus 0. Specific formal charges that we charge. Yeah, again, so this again with the formal charge. What this is going to show you on individual. Okay. So for sulfur, the typical amount of valence electrons that we said it has is 6. Threes. Just 11.5. So how many? 0. 2. Oh, I don't. That's most to charge. And actually the ones that have charge of this out. You're good so far?
Okay.
minus.
Now, this is still applying what I just taught. And Melissa, and you immediately look down like, no. Why?
But like,
Just so again, the formula, if you want to write this down, you can just put like FC, so formal charge, is equal to, valence electrons.
equals 0.
That exactly.
And
That's it.
Let's draw the Lewis structure for SO3. This is sulfur, each oxygen that has 8 valence electrons. The sulfur, it only has 6. So let's move 2 to the center here. We'll form a double bond. Now the sulfur, it'll have 8. This oxygen still has 8. So this is a valid Lewis structure for SO3, sulfur trioxide. When we're writing Lewis structures for things like SO3, where we have a sulfur, which is in period 3, We know that sulfur can have an expanded octet, so we really want to look at the formal charges here just to make sure this is the best structure. So if you look at the formal charges, they look like this. If you need help finding formal charges for sulfur trioxide, there's a link at the end of this close to 0. So if we Lewis structure for well, and so structure 3, don't draw this trigonal planar molecular geometry, which is kind of